It's Math and Beats, and you know what? This time, it's time to talk about derivatives of parametric curves. Let's get going in this video here. Alright, so we're going to do a little bit of refreshing at first. Let's recall, suppose that you got a point, x comma y, some point. And this point can be determined by the functions x is f of t and y is g of t, where f and g are defined on some interval I in terms of t. So essentially, remember that what we're really saying here is that any ordered pair x comma y on some curve in the xy plane, both coordinates x and y are both determined by some other variable, which we're calling t here. Now, of course, as we let t vary, both x and y vary. So they're going to move around in the plane, in the xy plane. And so this is our parametric equation setup. The curve that is produced by this type of situation is called a plane curve. So it's just a general curve in the plane, if you will, or, as I like to say, parametric curve. And this pair of equations, as we've described previously, x is a function of t, f of t, and y is a function of t, g of t, those two equations are what we refer to as parametric equations. So just kind of reminding ourselves of this right now. So for instance, let's just consider the parametric equations right here. You got that x is 3 sine of t and y is 2 sine of 2t. And you might be wondering, what kind of curve does that sketch out? Because every single ordered pair x comma y, x is determined by 3 sine of t and y is determined by 2 sine of 2t. Now, lucky for you, I got a little diagram to help us understand that here. So here is the curve that is produced by those parametric equations that we just saw. And so, as you see here, t is at 0, and we're at 0, 0. And you just imagine, okay, as I increase my t value, at any given xy here, it's determined by the particular t value. In that case, you see t is 3.54, and I can keep increasing this value of t, and as I increase the value of t, the point x comma y moves along the curve, if it'll move. There it goes. And as you can see, as t moves along, we go through this cycle here. Kind of almost looks like an infinity symbol, right? Kind of a nice looking graph. So that's just a reminder of parametric curves, right? Now it's like, what's our goal? We really want to find the slope of these parametric curves. So what does that entail? Like I said, the goal is we want to find the slope of any plane curve or parametric curve defined by the equations, the parametric equations, x is f of t and y is g of t. Now you go to a different diagram here. Here's that same curve that we were looking at earlier, right? And you think, okay, well, as we move along the curve, at any given value of t, x and y are going to be some particular ordered pair. And as long as the curve is nice and smooth, like in that piece right there, we should be able to find the tangent line at that point. And as I move along the curve, right, keep moving along, the t value, the parameter is changing, and the values of x and y are both changing. And at any given value of t, I should be able to find what the slope is at that particular x and y coordinates on the curve. So we'd like to figure out what that is. All right. So that's the goal. Now here's the thing. When we have parametric curves, parametric equations like we have right here, x is f of t and y is g of t, well, there's always some relationship between x and y, if you will. You know, if we wanted to, we could just draw the graph of y is x squared, for instance. And if we did that, think of this. X could just be t, and y could just be t squared. But since x is t, then y is actually x squared. And so what we're saying here really is that in all these different situations with parametric equations, let's consider that the function g of t here, which is the output value y, the vertical location of the curve, is just h of x of t. And that is, just think of it as h of x, but x depends on t. So there's this relationship between x and y determined through this type of rule, like the one we saw on the right. And so under that assumption, you think, well, what if I went ahead and just differentiated both sides of the equation with respect to t? So then if I did that, then on the left-hand side up there, dy dt, well, that's just the derivative of the function h of x of t with respect to t, but that's Chamberl's situation, assuming the differentiation process is taking place. And that is, differentiate the inner function x with respect to t, right there, times the derivative of the outer function h with respect to x. But of course, h is what we're calling y, right? Right up here. H is a function of x of t, which is just y. So the derivative of h with respect to x is really just the same as the derivative of y with respect to x. And thus, that's what we're saying. If I take this equation right here, and I just say dy dt is dx dt times dh dx, and I divide both sides of that equation by dx dt, guess what I get? dh dx, which is the same thing as dy dx, is dy dt divided by dx dt right there. And that's exactly what we're after, right? You go back to this curve over here, and at any given point in the curve, the slope, of course, of the curve is dy dx. How does the slope of this curve change as I move infinitesimally, left and right? What happens infinitesimally up and down? That's my dy dx. And thus, we get the formula right here that I'm about to circle, boom. And that exactly right there is our formula for the derivative of a parametric or plane curve at any given point, x comma y, given the parameter t. So what would we like to do now? We would like to look at a couple of examples of exactly how this might work. Let's do that. All right. So here's the first example. Let's find the equation of the tangent line to the parametric curves right over here, described by x is a function of t, which is t to the fourth plus 1, and y is a function of t, which is t cubed plus t. And let's do that. Let's find the equation of the tangent line of that parametric equations at the specific location t is equal to -1. So we know from what we just established, dy dx going to be dy dt divided by dx dt, right? How does y change with t? And then divide that by how does x change with t? Instantaneously, of course. So in order to find the equation of the tangent line to this plane curve or parametric curve, we gotta, of course, first find the derivatives of each of the individual functions with respect to t. So let's do that. All right, first things first. dy dt. What's it gonna be? Just differentiate this function over here with respect to t. That's just power rule. That's a 3t squared plus a 1. All right, and then we'll also need to find dx dt. So that's differentiating that function right there, x of t with respect to t, another power rule, just gives me 4t cubed. And so we need the equation of the tangent line. That means we need the slope of the tangent line. That means we need to evaluate dy dx at t is equal to -1. So let's figure that out. The slope of this curve, dy dx, at the location t is equal to -1 here, is going to be, all right, let's find that quotient. 3t squared plus 1 over 4t cubed, right? That on the numerator, that's my dy dt. On the denominator, that's my 4t cubed, which is dx dt. And I'm going to evaluate this at t is equal to -1. Plug in -1, what do we get? 3 times -1 squared plus 1 over 4 times -1 cubed, which is going to give me a 3 plus 1 over -4. Of course, that's 4 divided by -4. That's -1. And thus, we know that the equation of the tangent line of this parametric curve at the t location, the parameter location of t is -1, is, well, the slope is -1 there, ironically. Now, in order to find an equation of a line, in specific, in this case, a tangent line, we need to also know what point we're at on the curve. In order to do that, we need to find what x of -1 is, and also what y of -1 is, right? I'm just plugging in my t value into my x and y coordinates to figure out which ordered pair I'm actually at, so I know which point that this line will be tangent to. So plug in -1 into x, I get a -1 to the 4th plus 1, that's a +1 plus 1, which is a 2. And then plug in -1 into y, that's a -1 cubed, and then plus a -1, that's a -1 minus 1, which is -2. And so using point slope formula and the ordered pair we just found, x comma y, we get y minus a -2 is equal to the slope, -1 times x minus 2. And notice distributing the -1 on the right-hand side gives -x plus 2. And on the left-hand side, we have a y plus 2. And if I minus 2 on both sides, guess what I get? Y is equal to -x. So there you go. That is the equation of the tangent line to this particular plane curve. Now you might be wondering, what's that look like? Well, lucky for you, got a picture right here. Bam, there's our plane curve that corresponds to the parametric equations we were just looking at. That's the blue graph here, right? There's my x comma y's. And here's the ordered pair, 2 comma, bam, -2, like we just said. That's the point we're interested in. That is when, of course, t is equal to -1. And as you can see, we have that the equation of that red tangent line there is y is equal to -x. And that line, of course, goes through the origin and has slope equal to -1. And there you have it. See? It's like kind of like an implicit curve, but instead it's defined in a different way. And so we should still be able to find a slope to a nice smooth curve at the points for which their slopes are actually defined. Let's look at one more situation. Here's another situation. We have the parametric curves given to us here. Bam, right down here. X of t is 2t cubed plus 3t squared minus 12t. And y of t is 2t cubed plus 3t squared plus 1. So the first two terms are identical, right? But that third term in each of the coordinates changes how this behaves. Now, we'll see the graph here in a bit after we do a couple things. But, you know, the whole point of what we're trying to do is, given these parametric equations, can we find all points on this curve for which the tangent line is horizontal. Now, what does that mean? If the tangent line is horizontal, then of course, dy dx, the slope of the curve, should be 0. So what we need to do is figure out what the slope of this curve is at any given value of t at any given order pair x comma y, and then set it equal to 0 and figure out when that's true. So let's do that. Again, we find dy dt because, just as another reminder, up here towards the top, dy dx is going to be dy dt over dx dt, like we've established in this video. And so dy dt here, differentiate y of t with respect to t. What do we get? 6t squared plus 6t, power rule. And then, moreover, dx dt is going to be 6t squared plus the 6t. But now that last term on x minus 12t gives me a minus 12. And thus, dy dx is the quotient, dy dt, which is 6t squared plus 6t over 6t squared plus 6t minus 12 on the denominator. And I think, okay, well, if my tangent line is going to be horizontal, then this slope, dy dx, must be equal to 0. And that must mean my numerator must be 0, while simultaneously my denominator is non-zero. So let's just rewrite this, factoring out the numerator and denominator. What do we get? In the numerator, I can factor out a 6t, and I'll be left with t plus 1. And in the denominator, I can factor out a 6, which will leave me a t squared plus t minus a 2. And even furthermore, this is going to be a 6t times t plus 1, all divided by 6 times t plus a 2 times t minus 1. So you see, we don't have any common factors in the numerator and denominator, and thus the only time that this slope is going to be equal to 0 is if the numerator is 0, since t is equal to 0 and t equals to negative 1 does not make the denominator 0, and thus we get t is 0 and t is equal to negative 1. And thus, those are the values of t that make the slope 0, the slope of the tangent line to this plane curve, equal to 0, making the tangent line, of course, horizontal. But remember, we were asked to find the points, so that's the ordered pairs. So we got to plug these values back into x and y. So when t is 0, what happens? All right, x of 0 is going to be equal to just 0, right? 0 times 0 times 0. So it's just 0. Y of 0 is going to be equal to 1. And thus, one of the points is 0, 1, as we can see right there. The other location of t is equal to negative 1, gives, well, a little more involved now, x of negative 1, plug it in. We'll get 2 times negative 1 cubed plus 3 times negative 1 squared minus a 12 times negative 1. What do we get? Negative 2 plus 3 plus 12, and that is a 13. Also, plug in negative 1 into y. We get a 2 times negative 1 cubed plus a 3 times negative 1 squared plus a 1. Of course, that's negative 2 plus 3 plus 1. And what do we get? 2. And so the other ordered pair is, well, x is 13, y is 2. So there's these two ordered pairs on the graph of this parametrically defined curve that we see above, for which the tangent line is horizontal. Let's take a look at the picture here. Look at this picture. It's kind of a nice looking graph. That's the parametric curve that we just talked about. And as you can see right there, at 0, 1, the slope is 0. At the ordered pair, 13, 2, the slope is 0. and hence we have tangent lines that are horizontal, and that was exactly what we were asked to find. Now, one last thing we're going to do here is, how about let's find all the points on the curve where the tangent line is now vertical, right? So what is that going to entail? Well, if the tangent line is vertical, then the slope will be infinite in nature, and thus we should look for values of t that make the denominator in the derivative 0 and the numerator in the derivative non-zero simultaneously. So remember what our derivative was. It was right there, right? And so what I'm going to do is take a real quick picture of this. Bam, take that picture. I'm going to copy it, and then let's just throw it right down here, because you know what? That we got to use that. Can we? There we go. Ha! Got it. So there it is. All right, 6t times t plus 1 over 6 times t squared plus t minus 2. Of course, that's 6t times t plus 1, all divided by 6 times t plus 2 times t minus 1. And that, remember, was our derivative of y with respect to x for this parametrically defined curve. And as we can see, like we already stated, there is no values of t that make the numerator 0 and denominator 0 simultaneously. And thus, the values of t that make the denominator 0 are going to be the values of t which result in a vertical tangent line to the curve that we're looking at. What are those values? When does this denominator equal 0? Well, that's going to be when t is negative 2 or t is equal to 1. And again, we want to plug those values back into the parametrically defined equations, right? So what is x of negative 2? What is y of negative 2? That's what we're after. And of course, what is x of 1? And what is y of 1? That's what we're after, those actual ordered pairs, since that's what's going to determine where we're actually located on our curve itself. Well, it ends up that if you plug this value of t, again, into our values up here of x and y, then what will you get? You will get a situation that looks just like this. And that is, here we go. Look at the curve. It's the same curve we looked at a moment ago. And as you can see, there's these two locations of t for which the curve has a vertical tangent line. And in fact, this point right here is the ordered pair negative 7, 6. And this ordered pair right over there is the ordered pair 20, negative 3. And those are both the result of plugging in t into the corresponding parametric equations that we have that defines the curve that we see in this plane curve. And there you go. There's a little sense of how to find derivatives of parametrically defined equations which result in these plane curves. And as long as we have a nice and smooth curve, we should be able to find these derivatives, as we can see in this video right here. So in terms of this video, that's it. That's the end of this discussion. And until next time, you know, it's Math and Beats. I'm out.